Hello everyone, welcome to this video. It's a continuation of the discussion on statistical process control and control charts. This one's on one specific type of control chart called the P chart. P is for proportions. And this is, again, I'm hoping you're following my videos. You've been watching the previous couple on the R chart and the X bar chart, because this video is going to be very similar. Where I'll start off reminding you, as I have in the past few videos, what a control chart is, and examples of control charts, and then some, the ways we're going to interpret the control chart, how we're going to look at a control chart and determine whether or not a process is statistically stable or within statistical control. And then I'll get into I do have a couple examples, right? So this will be a little bit different than the R chart and X bar chart videos in that I'll have two examples instead of just the one. Okay. So again, control charts. A control chart, or Shewhart chart, named after Walter Shewhart, who first introduced these in 1924. A control chart of a process characteristic, such as a mean or variation or some attribute, what proportion of the samples are defective, or what proportion of the samples are blue, or what proportion of the samples are greater than 5, or whatever. We're going to see that kind of a chart today when the characteristic being monitored is some proportion of some attribute. So a control chart of a process characteristic consists of values plotted sequentially over time. And there's your horizontal axis, vertical axis, horizontal axis. The horizontal axis will typically represent time, in days or months or years or whatever. And the vertical axis will represent these characteristic values, right? The ranges, the means, the proportions, the standard deviations of the samples I'm looking at, etc. So you have these dots connected by some segments here, a little line chart. And the way these are plotted, is each day or each hour or whatever, each time unit, a sample is taken, a sample of data. And then, for our charts, the range of that sample was recorded. So the range of sample 1, the range of sample 2, the range of sample 3, sample 4, sample 5, etc. And you made the line chart that way. For X bar charts, right, the mean of each sample was recorded, the mean of sample 1, the mean of sample 2, the mean of sample 3, and so on to complete the line chart. Today, we're going to be talking about P charts, where I'm going to take every day or every time unit, day, month, year, whatever, every unit of time, a sample will be taken, and then we'll record what proportion of that sample has a certain attribute. Now, my examples today, it's going to be some manufacturing samples. Most of these, a lot of control chart applications are in businesses and manufacturing and service industries. So the attribute I'll be looking for today is what proportion of the sample is defective, is not working properly. That'll be the attribute I am monitoring. Right, the numbers of defective objects that have been manufactured. So the proportion of defects for sample 1, the proportion of defects for the sample 2, proportion of defects for sample 3, sample 4, sample 5, and so on. All right, and then as with any other of the charts we've seen, control charts, there will be these 3 lines in the chart. The middle line being, the center line being the mean value of all the sample proportions, or the mean value of all the sample ranges, or the mean value of all the sample means, right, depending on what value, what characteristic you are monitoring. So there'll be a center line, and then above that and below that you'll have a line representing your upper control limit, or UCL, and below the center line the lower control limit, or LCL. Now with the R chart and X bar chart, these were found using a table. Today with the p-chart, they're found using a pretty simple calculation, and no table is required. Now you'll have to know the formula or have a sheet in front of you with a formula. Most of the time, I'll probably, it'll be a formula sheet would be provided. But it's a very simple calculation that doesn't require the use of a table. And these upper control limits and lower control limits and center line are useful lines to help us look at a chart and determine whether or not the process we're monitoring is statistically stable or within statistical control. And I'll talk about the criteria for that in a minute. Alright, so some examples of charts. Now, again, we've seen a couple of these in my previous videos. We had a chart for monitoring the variation of a process. Now, there was the R chart, which you put down, you labeled the sample ranges. Now this was typically used, the R chart, this is typically used when the sample sizes are small, and in the book I'm looking at, that's less than or equal to 10 objects in each sample. For larger samples, you may wish to monitor the standard deviations of the samples, right? But still monitoring variation, right? Range, standard deviation. There were some charts that would monitor the center of a process or the means of a process. I'll say center actually, because you could do an X bar chart where you're monitoring the sample means as time goes on, or you could do a median chart where you take each sample and label the medians of each sample as time goes on and monitor that. But today we're doing a control chart for monitoring certain attributes, and again, the attribute that I'll be looking at today is the proportion of what objects are defective or not working properly. This is a P chart, right, for proportions. And then and of course there are many more. There are other things you could monitor in a process besides these three, all right? But these are the only three: R chart, X bar chart, and P chart that I'm actually going to do videos on for my introductory statistics. Alright, so how do we read a control chart or interpret a control chart in order to determine if a process is stable or not? So interpreting control charts, a process is not statistically stable if one or more of the following out of control criteria are satisfied. So one, if you notice in the data, right, when you make your little line chart, if you notice that there's an obvious pattern or some obvious trend or obvious cycle in the data, then that kind of a thing doesn't happen naturally, right? Not if it were truly a statistically stable system. So if you see the data seem to be tending upward or tending downward, or there's some obvious upward shift or downward shift in the data, maybe there's an increase in variation. It starts off, the data is kind of packed together, and then it gets wider and wider and wider as time goes on. You don't like that. Right? That is not good. That's definitely unstable behavior. Maybe the data, all the data points are close to forming a straight line, or they're close to forming a parabola shape or a wave or a sawtooth pattern. If there's some obvious pattern or trend or cycle in the data, that's not a good thing. Right? We'll say that the process we're monitoring is not a stable one, not in statistical control. Number two, at least one point is above the upper control limit, right, the UCL, or at least one point is below the lower control limit. Right? So looking back here, that's what the upper control limit and lower control limit will help us with. If any point falls higher than that, they'll be considered an exceptionally high point, a significantly high point, and the process will deem unstable. Same thing for below the lower control limit. We notice any points down there, we'll deem the process unstable in that case as well, and something would need to be fixed to try to get stability back. And then the last one here, the run of 8 rule, and as I've mentioned in previous videos, I've seen run of 7 in some books, but the book I'm kind of referring to here is the run of 8 rule. So if there are at least 8 consecutive points, all above the center line, or at least 8 consecutive points all below the center line, will determine that the process is unstable. Right? And again, a way to think about this is think about flipping a coin. Right? When you flip a coin, you're either getting heads or tails, right? So if you think about looking at a data point in a line chart, it's either going to be above the center line or below the center line. Well, if you flipped a coin and got 8 heads in a row, the chances of that happening are incredibly slim. So you'd probably think there might be something up with this coin. It might be an unfair coin or unbalanced coin. Same thing with a process like this. If you're looking at it and you notice a run of 8 consecutive points above the center line, or 8 consecutive points below the center line, the chances of that occurring naturally are very, very slim. So we would reasonably deduce that this process is more than likely out of statistical control. It's not stable, not balanced. And then I would go in and try to figure out what went wrong and how to fix the process. All right, and please note that these aren't the only conditions that, and some companies use additional criteria. Some other authors, of other textbooks use additional criteria, but this kind of sums up a lot of what you're looking at, a lot of what you're looking out for. A lot of it's in number one here. This concept of, is there an obvious pattern or obvious trend or obvious cycle? That could mean a lot of things, but you're just looking for things that wouldn't normally occur naturally. All right. So now that I've reintroduced control charts, gone over the same pages I've gone over in the previous couple videos, let's get to the one specific control chart we're working on in this video. And that is a control chart for attributes, right? The P chart. So a P chart, or control chart for P, for proportions, is a graph of proportions of some attribute plotted sequentially over time, right? Just like any control chart. So some notation involved here. Now this lowercase n you've seen in the R chart video, the X bar chart video. N is the size of each sample or subgroup, right? Now be careful with this. It's not the entirety of like all sample values taken. This is the size of each subgroup, right? If I were, say my time units were days and I was looking at groups of objects from day to day, n would be the size of the sample I took each day, not all the samples together. All right. So the size of each sample or subgroup. P bar, just like R bar for R charts and X bar for X bar charts, X double bar. P bar is the mean of all the sample proportions. So you add up every sample proportion and divide by how many samples you had. Now, this will be equivalent to what I have down here if each sample has the same size, right, which we're going to be working with. We're going to assume that every sample every day, or every sample that I take every time period, is going to have the same size. So if you want to do this, you could add up all the sample proportions and then divide by how many there are. Or if each sample has the same size, you could just take the total number of items with the attribute you're looking for, right? So like in this case, in the examples I'm going to have in this video, we're going to look at the total number of items that are defective, that aren't working properly, and then divide that by the total number of items sampled over the entire time period. All right. You can think of it this way if you want, but I'm just going to stick to the mean of all sample proportions. Okay, and that's P bar, right? P bar. And then you'll see a Q bar, which, if you recall proportions, and there was P's and Q's, Q was always 1 minus P. Same thing here for Q bar, right? When you see a Q bar showing up later, Q bar is just 1 minus P bar. All right, then on the chart itself, right, those 3 lines, the center line, the upper control limit, the lower control limit. Where are these values for these three lines? All right, so the center line is at p bar, right, that mean value, right, the mean value of the proportions. And then the upper control limit and lower control limit, you're going from the center line and adding and subtracting 3 standard errors of the proportions. So like 3 standard deviations above, 3 standard deviations below. You may have heard somebody refer to 6 sigma before. This is related to that. I'm not going to get into that though. So here's how the upper control limit is calculated. P bar plus 3 times, and then your standard error for a distribution of P bar, 3 times the square root of P bar Q bar over N, right, where I showed you the P bar and Q bar earlier, and N again is the size of each sample, not the entire, not everything, just each particular time period sample. Then the lower control limit, or LCL, is just minus, subtract that 3 standard errors. P minus 3 times the square root of P bar Q bar over N. All right. And then we'll look at our chart, draw these lines, and make a determination as to whether or not the process that we're monitoring is in control or not, or if it's stable or not. Now, another thing I want to point out is that just because a process is in control doesn't mean it's a desirable process. Just because a process is in control, that means all the data points are, consistently around each other. They're pretty balanced. But that doesn't mean that the particular specifications of the manufacturer are being met. Yeah, they all might be pretty consistent, but they might be consistently off of what the manufacturer specified needs to be the correct measurements. Right. So I'll say that again. Just because, and we're going to see this in my first example, just because a process is in control, and I'll write this later, doesn't mean that it's a desirable process. You still might want to fix it. All right, so let's take a look. So my first example involves minting, just like my R bar, just like my R chart and X bar chart videos. I'm not using the same chart this time, but it's still the same kind of example. So let's consider a process of minting quarters, right? So suppose we go to the, I don't know why, but the first one I always think of is the Denver Mint in the United States. Listed below are the numbers of defective, right? This is the attribute that I was talking about. Right. Listed below are the numbers of defective coins in successive batches of 100 coins randomly selected on consecutive days of production. Right, so I'll actually write that off to the side here. So the attribute that I'm monitoring here is being defective, not working properly. Right. And so when I see P down here, right, in my chart that I'm going to fill in this row of P's. P is the proportion of defective items. In this case, the proportion of defective coins, right, in my sample, in each sample. And what was mentioned to me too was that every day there was a batch of 100 coins being sampled, right? 100 coins was randomly selected. So that would be the value of that lowercase n, right? The batch of 100 coins being sampled each and every day. So my sample sizes, right, the subgroup sizes is 100. So here's how I'm going to read this chart, okay? So the mint, say again, the Denver Mint, they produce a bunch of coins. Obviously, they produce more than 100 coins, 100 quarters a day, right? I should have said quarters, not coins, but they're coins. But they're gonna try to monitor defectiveness, right? They're monitoring an attribute of these coins and seeing if the process is stable or not when it comes to that particular attribute. So on the first day, right, they take 100 randomly selected coins that they've minted, 100 randomly selected quarters, and then they measure them, they weigh them, if they see how many of them don't meet the specifications within a certain margin of error. Right? How many are defective, are not created properly. So on day one, they pull 100 coins at random, and they find that 32 of those 100 are defective. So what is the value of P? It's just 32 out of 100, or 0.32. Right, it's just 32 out of 100 would be the P value. Now it's not P value like a hypothesis test, right? It's just proportion. All right. Second day, same thing. They produce a bunch of coins all day long. They take 100 random coins and maybe measure their circumference, their weight, their thickness, and see if the coins fall within the specification guidelines for the U.S. government or something, or if it's the Denver Mint. And they find that 21 out of the 100 that day are defective, right? So 0.21, 21 out of 100, right? And then 25 out of 100 for the next day, 0.25, 19 out of 100 for the next day, 0.19, 35 out of 100, 0.35 for day 5, 34 out of 100, 0.34 for day 6, 27 out of 100, 0.27. Right? All these are just, move the decimal place to the left 2 points. So 0.3 or 0.30 for day 8, 0.26 for day 9, 0.33 for day 10. Now, what we're going to see here is that these are all pretty consistent. So you're going to see that the process is stable. We're going to see that in a minute when I look at the P chart. But these numbers are incredibly high for, especially a government mint. This would be very wasteful if I wouldn't, if I went through, these look all around maybe 25-30%. If 25% of every quarter that was minted was defective, that would be bad. All right, there's something wrong there. So you still have to use your judgment. All right, we're going to see in a minute when we look at the P chart, we'll say that this process is in control, right? These numbers are consistent. But then if you think about it, would the process be satisfactory for a government coin mint? And like I said, these numbers are incredibly high. You would hope that at a government mint, out of every 100 coins, maybe 1 or 2 of them are defective, not 30, not 25 or 30. So remember what I was saying earlier, and I'll write it later. Just because a process is stable doesn't mean it's satisfactory, doesn't mean it's a good process. All right? Just means it's consistent. But it might be consistently bad, like this is. All right? So, and take that lesson too into my previous videos. I don't know if I had mentioned that before. Okay, so let's take a look. Let's make a P chart. Now I'm going to do this on the calculator here instead of drawing it by hand. I mean, I know there's only 10 of them, but still, I feel like, just like with my previous R chart and X bar chart videos, doing these by hand isn't the greatest. You can, it's not impossible, but I'm going to do it on my TI-84 here. Now what I've already done this ahead of time, is you go to the stat menu and then hit edit, and you see list, let me go to list 1, 2, 3. So list 1 has the day numbers, right? Just day 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. List 2 has the number of defects. Right? Remember there was 32 on the first day, 21 on the second day, 25 on the third day. And list 3 has their proportions, right? So again, just moving dividing all these by 100. All right. So I've already entered these, and I've set up a stat plot. So if I go to y equals, see plot 1, plot 1 is on. I've set up a plot where you're going to see these plotted out. So I'm going to go zoom 9 for stat plot, and there you go. Okay. And again, I'll hit the trace button here, and we can see on the first day 32.32 the probability of defects in that first sample. The second day sample was 21% defective. The third day sample was 25%. All right, so this is a good P chart, right, where the horizontal axis is the days and the vertical axis the up and down. There is no axis, you can't really see it, but the second values are all proportions, right? All right, now what I'm going to do is I'm going to put in the 3 lines, right? The center line, the upper control limit, and lower control limit. So, oh yeah, and I've already mentioned n is 100, right? Keep that in mind. N is 100. Each day had a sample of 100 coins. All right, so what is the center line for this particular P chart? Remember, that was that P bar. Now you can do this a couple ways. Because every sample was the same size, you could add up all the defects and then divide it by 1,000. You can add up 32, 21, 25, 19, 35, 34, 27, 30, 26, and 33. Add those up and then divide by 100 times 10, right? There were 1,000 total objects. Or just because, again, the sample sizes were all the same, you can just do the average of these P's here, right? Take the average of the P's, the mean. This is, again, the mean value of the sample proportion of the P's. Right, so let's see what that is. Now I've got those were in my list 3. Alright, so get out of here. Those were in my list 3. So if you go to list above the stat button, over to math, you can find the mean value of a certain list of data. And as I mentioned, down list 3 were all those proportions. Alright, so it was 0.282. 0.282. And let me graph that. Let me go to the y equals 0.282, and look at the graph now. So there's my center line. Now there were only 10 values here. There's only 10 data points, so that run of 8 isn't going to happen, right? That run of 8 rule. Notice I am not seeing more than 8, any place in this graph where there's 8 in a row below the center line or 8 in a row above the center line. So far looks pretty stable to me, right? And it's not getting wider as you move to the right. It's not always increasing, not always decreasing. I don't notice any obvious pattern. I don't notice any obvious pattern here. And again, that run of 8 rule isn't happening. So far it seems like the process is in control. It is stable. But let's put in those upper control limits and lower control limits. Now, one thing I didn't mention about the upper control limits and lower control limits for proportions. Remember, the upper control limit is this P bar plus 3 times the square root of P bar Q bar over N. One thing I failed to mention earlier, remember, this is proportions. These are for upper limits and lower limits for proportions. Remember, a proportion is a percentage. You can't have a proportion higher than 1. Same thing for 0. You can't have a proportion lower than 0. So if this is higher than 1, if this ends up being greater than 1, this calculation, then you're going to use the number 1 instead. All right. I'll say 1.0, right? Because you can't have a proportion higher than 1. So it doesn't make sense to say that the upper limit is 1.3. All right, I hope that makes sense. Again, that's only because these are proportions. There wasn't a rule like this for R and X bar charts, right? This is only for proportions. And the lower control limit, same thing, but involving 0. I take this p bar and then I subtract 3 times the square root of p bar q bar over n. And same thing here. If this calculation ends up being lower than 0, if it ends up being negative, then the lower control limit, you just simply have be 0, because you cannot have a proportion lower than 0. So I hope that's clear. Sorry, I failed to mention that earlier. All right, so let's calculate these. So the upper control limit is 0.282 plus 3 times the square root of 0.282 times, and then 1 q. Remember, q bar is 1 minus p bar, right? So 1 minus 0.282 be 0.718. Right? And just make sure that those add up to 1, and they would. Divided by n. Now remember, n is that size of each sample, each time period. In this case, it's days. N is 100. I mentioned that earlier. Every day, 100 coins is being selected randomly. And we'll get an approximation to this, and I'll do the same thing for the lower control limit. That's 0.282, the p bar, minus this, minus 3 times the square root of 0.282 times 1, q bar, 1 minus 0.282, 0.718, divided by that n. Again, you're taking 100 coins a day, right? That's the n. All right, let me enter these. Now I'm just going to enter one of them and just change the plus to a minus sign for the other one. Right, so I get out of here again. So I'm taking 0.282 plus 3 times the square root, and then I make sure all of this is in the square root. Okay, 0.282 times 0.718, and then divided by 100. All right, just make sure that that square root symbol is extending over all of this. All right, we're getting approximately 0.417, right? Because the other one's the 3 decimal places. So let's make this one the 3 decimal places as well. Approximately 0.417, and that's not higher than 1, so this is okay. All right, I'm going to put this in as my upper control limit. All right, then I'll re-enter this. All right, go second entry above the enter sign, just second entry, and it gives me the same thing back, and I can just scroll back through it and change the plus sign before the 3 there, the 3 times the square root. Change that to a minus sign and recalculate 0.147, approximately 0.147, and that is not lower than 0, so this is a good lower control limit. All right, and let me graph these. All right, I'll put these up as lines on my graph. So back on the calculator, I go to y equals. There's my center line, right, the average of the p's, that was 0.282. My upper control limit was approximately 0.417. My lower control limit, approximately 0.147. Let's see if those show up on my graph. Alright, and they don't, so I'm going to change the window so that my y min, see it's from 0.16 to 0.37. The lower control limit and upper control limit wouldn't be showing up. So I go down to y min, and I'll make this, my lower control limit was 0.147, so let's make the y min 0.14. So I'll be able to see the lower control limit line. And the upper control limit is 0.417. So just so I can see it, I'll make the y max 0.42. Right. There's the center line, there's the upper control limit, the lower control limit, and you notice again, there are no points above the upper control limit. There are no points below the lower control limit. There's no obvious pattern I'm seeing. And it's not always increasing, not always decreasing. There's no giant vertical shift. There's no giant, upward shift or downward shift. They don't form like a straight line or a parabola or a wave, or there's no run of eight points all above, 8 consecutive points above the center line. There's no run of 8 consecutive points below the center line. There's no point above the UCL. There's no point below the LCL. It looks like, I just looking at all these criteria, I would say the process is, going back to this question here, determine whether the process is in statistical control. I would say yes, the process is in control. The process is statistically stable. All right, now here comes the big part though. All right, I mentioned this earlier. Big note, big note. All right, I'm going to put it at the bottom here. Just because a process is in control doesn't mean that it's a desirable process. Just because a process is in control, right, or consistent, that does not mean that the process is desirable. Because the process may be producing things that you don't like. You know, it might be consistent, sure, but the process might be producing things consistently that you don't care for, that aren't within your company's parameters or the company's manufacturing specifications or whatever. That the process does not mean that the process is desirable or satisfactory. Right. So let's look back here, right? So yeah, I mean, looking at the graph again, right, looking at the P chart, right, looks pretty stable to me, right, these proportions of defective items. But, as I mentioned, all of these numbers are pretty high if we're talking about defectiveness, right? These are all pretty high for, defectiveness. We don't want 30%, 25% of the coins that we produce to be defective. That would be a huge waste of materials. You know, like I mentioned earlier, if we were a government mint, something with high standards, I would expect out of every 100 coins there to be maybe one or two defective coins, not 32, not 21. So sure, the process is consistent, the process is stable, but it is consistently bad. All right. So the process is stable, but would the process be satisfactory for a government coin mint? No. The process consistently produces too many defective coins. Well, let's say too many defects for what I would want, right? I would want a lot fewer defects than what I'm seeing in these 10 days samples. So even though a process is stable, is consistent, is in control, you still have to use some common sense, right? You still have to use some logic to look at the numbers and see if if they're meeting the specifications you actually want. Right? I hope that was clear. I really do, because that's something to look out for, and that's something you might be asked about. All right, is the process stable or not? And even if it's stable, do you still like the process? Does the process meet your needs? Here, this particular procedure doesn't meet the needs that a government mint would need. Right? I need much fewer defects than this. So I need to go in and get new machines or repair the old ones or hire new people, whatever. All right. So be careful. Okay. Now, another example, another one involving where the attribute being monitored is again defectiveness. All right, so this one's another manufacturing problem, kind of like minting coins, but this time manufacturing heart defibrillators. All right, which again, if you were a manufacturer, a company that made heart defibrillators, you would want very few defective heart defibrillators to be going out to market. Because you send too many defective heart defibrillators out, you're going to get sued very quickly by people who went to use your defibrillator and it wasn't working. Right? In fact, you'd want practically no defective items, but that's neither here nor there. Right? We're not actually running a defibrillator manufacturing plant or whatever. But let's just take a look at the problem. Right? So listed below are the numbers of defective heart defibrillators in successive batches of 1,000 defibrillators randomly selected on consecutive days of production. Right? So this is 20 days in a row. 20 days in a row, 1,000. Right? This is batches of 1,000. So that's the value of n here. Right? N is 1,000 this time. Right? Each day has a sample of 1,000 of these defibrillators that are pulled, and then they're tested. These 1,000, they're maybe their batteries tested, or how they operate, their measurements, right? Whatever, to see if they meet all the specifications that the company has. Now, this again, the attribute here, right? Just like the last problem, the attribute being monitored is defectiveness. Right, or numbers of a defective product, right? And the value of P, right? The P, the proportion of is the proportion of each sample that's defective, right? Proportion of defective objects, right? Defective defibrillators. Okay. So here's what's happening, right? So on the first day, this company, they produce a bunch of defibrillators, and they randomly select 1,000 of the ones they produced that day, and they found that 8 of them were defective. Okay. So the proportion would be 8 divided by 1,000, right? So 0.008, right? You move the decimal place to the left 3 places when you divide by 1,000. Next day they do it again, right? And then that's less than 1%, which again, depending on their tolerance, may be good or not. They might want less than 0.5% on average, or less than 0.25%. Again, I'm not worried. I'm not specifically looking at any particular company out there, right? So second day, same thing. 1,000 defibrillators are taken at random. They test them, measure them, whatever. 5 of those 1,000 were defective. So the proportion of the second day sample that's defective is 0.005. 5 out of 1,000. Then 0.006. Then 0.004, 0.009, 0.003, 0.012, 0.007, 0.008, 0.005, 0.022. Yikes, that's 2%. That's pretty high. That's probably going to come back to bite them. Right? 0.004, 0.009, 0.01, 010, 0.011. That's also 1%, 1.1. Again, if you're making defibrillators, these are things that could save people's lives. Having 1% defectiveness is not good, right? Anyway, but that's not the question, though. Right? The question is going to be, is the process stable? Not, do we like it? I mean, you could ask that question after. Do we like the process? Are things being manufactured properly? To our liking. But again, we'll ask the first question first. All right, so 0.008, 0.007, 0.006, 0.008, and 0.005. Right, so there's 20 days in a row they took 1,000 of these defibrillators and determined how many, found how many of these 1,000 weren't working properly, and found the proportion for each day. Okay, so now the question is, as with the last one, I'll start off with determine whether the process is within statistical control. Is this procedure, are my machines, is the procedure of manufacturing these defibrillators statistically stable? or is something out of whack and I need to go in and fix the procedure. Now, I'm telling you right now, based on these numbers, and being that these are defibrillators, right, very important pieces of equipment, this 11th day is striking me as high. All right, 2% defective on one day, that's wrong. All right, that can't fly. But again, that's not what I'm worried about. I'm just asking, are the numbers consistent enough? All right. Then after that, we could ask the question, do we like the procedure as it is, the process as is? Okay. So again, I went through and put these numbers in a calculator. I put them in my calculator already. So let me show you. I go to the stat button here and edit. And you see my list 4, 5, and 6. Now list 4 is the day numbers, days 1 through 20. Alright, list 4 is 1 through 20. List 5 is the number of defects out of 1,000, right? So 8 on the first day, right? 5 on the second day, 6 on the third day, 4 on the fourth day, 9 on the fifth day, just like in my chart. Alright, I got all 20 of those numbers entered. And then list 6 here is all the proportions, right? 8 divided by 1,000, 5 divided by 1,000, 6 divided by 1,000, 4 divided by 1,000, and so on. Okay, all the numbers I wrote at the bottom here in the P's. Right. And then I've made a P chart. All right, that is plot 2. So I got y equals here. I'll go turn plot 1 off. And I've already set up plot number 2. Turn that on. So that, and I'll clear these guys because these are the center line and upper control limit and lower control limit from my last example. So I'm turning plot 2 on, going zoom, stat, and there's the 20 different proportions from the 20 days. And if you'd like to take a look at them again, I hit the trace button. See, on the first day, there's the proportion of defects on the first day, 0.008. Second day, 0.005. Third day, 0.006. Exactly the same as my chart here. Okay, for all 20 days, right? All 20 of these blocks here, 20 of these points. And yeah, as I suspected, now again, I haven't verified it yet. We don't have the limits yet, but I'll get them. See, a lot of them are pretty condensed. It seems pretty consistent, right? Seems pretty consistent, but then whoa, this point here. And you guessed it, that's day 11. That's day 11. Let me scroll through here. Day 11, right? With that 2.2% defective rate. Yikes, right? And that seems to be way high compared to the rest of them. Now, again, I haven't totally verified that it is above the upper control limit, but we'll see in a minute. All right. So what I'm going to do is calculate those lines. What's the center line, the upper control limit, and lower control limit, and I'm going to graph them on this chart here. All right. So I go to my y equals. Well, let me get out of here. Let me go back here. I'll clear this stuff. All right. So what is the center line? Remember, that was that P bar, and that's the average. That's the mean value of all the P's, especially if they all have the same sample size. Or you could add up the number of defects. You could add up 8 plus 5 plus 6 plus all the way to 5 here, and then divide by 20,000, right? Because there was 1,000 each day. Or just take the mean value of all the P's, right? Which I'll just do in my calculator because I already have them entered. So I go back to that list menu, right? Over to math, and then the mean value. Now the list that has all these proportions in them is my list 6, right? So just pay attention to what list. I just go second 6. There's L6 showing up. 0.00785. 0.00785, and let me graph that. Right. Y equals 0.00785, and look at this on the chart. Right, there's the center line. Now I do not see a run of 8 that are all above the center line or all below the center line. Like the first, looks like 1, 2, 3, 4 are below, then the next one's above, so that breaks that off. Then the next one's below, then above, then below. maybe above, below. I mean, I could use the trace button to figure it out, but I'm not seeing one of those runs of 8, right? 8 consecutive points all above the center line or all below the center line. All right, so far the process, when it comes to this attribute of defectiveness, the process looks like it's stable so far. Right? We haven't finished it yet. Right? Because again, I'm noticing this pretty high point that will probably throw everything off. All right, so let's calculate what's the upper control limit. Remember, the upper control limit is that p bar plus 3 times the square root of p bar times q bar divided by n. And remember that n is 1,000, not 20,000. Right? There's 1,000 a day, 1,000 in each subgroup, each sample. So that's this 0.00785 plus 3 times the square root of 0.00785, right, times, and then q bar is 1 minus p bar. So 1 minus this, so 0.99215. And again, just make sure that these both add up to 1, and they would, right? Divided by the n, right, the size of the samples every day, that was 1,000. All right, let's see what this gives me. And if this is bigger than 1, remember, if this is bigger than 1, I'm not using it. I'm just going to use 1 as the upper control limit. I don't think it will be, though. All right. So let's see. Let's calculate this. Go back. Let's take 0.00785 plus 3 times the square root of 0.00785 times 0.99215 divided by 1,000, and make sure all of that, p bar times q bar divided by n, make sure all of that is inside the square root, that square root's extending, or you put parentheses around it so it's in the square root. So the upper control limit is approximately 0.0162. Right, so let me enter that. Go to my y equals here, second line, second equation there, y2 equals 0.0162. And let me just graph it right now. Hey, look at that. I don't need the lower control limit. Don't need it. Look, there's the center line, and then I told you, right, that 11th day looked way out of whack with the 2.2% defective rate, and that's definitely above this upper control limit, right? This 3 standard deviations, standard errors away from the middle. It's further up than that. So right there I'm seeing, hey, this is out of control. But let me just put in the lower control limit while we're at it. All right, so what's the lower control limit? Again, it's just p bar minus 3 times the square root of p bar q bar over n. Now I'll just re-enter this and put a minus sign instead of a plus. Right, so back to the main calculation screen, second entry. Scroll back and change the plus sign to a minus sign. Right, that plus sign before the 3 there. All right, but it's negative. This is negative 0.0005, whatever. That's less than 0. That's not good. All right, you can't have a proportion less than 0. So the LCL is 0. All right, LCL is 0, not negative. All right. Okay. So back on my graph here, right? There it is. I mean, you see that axis? That's the x-axis. That's y equals 0. So there's the UCL, the center line, the LCL, and we're seeing that this process is out of control. It is unstable because of that 11th day, as I had suspected earlier. All right. So back to my page here, determine whether the process is within statistical control. The process, this manufacturing process, this process in which I manufacture defibrillators, the process is not within statistical control. in fact, looking at that chart, right, looking at that P chart there, I would say, hey, I'd seem pretty consistent for a bit, but that 11th day, I'd go back to see maybe who was working that 11th day or what machines were being run the 11th day. Or just go back through the whole process itself, look at every day for the past 20 days and see what went wrong. Why were there so many defects that day? And and then I would try to maybe repair the machines, see who was working certain days, maybe try to talk them up, maybe give them a talking to, see if they can elevate their work, or possibly let go. But just saying, there's got to be something I can do to fix the fact that this process is out of control. I need more stability. I need fewer days like day 11, right? I need fewer days with I need more days with fewer defects, right? And then after I've made the repairs, after I've made the tweaks, I might do it again for another 20 days, right? Do the same monitoring and see if the process is stable then. And then even if the process is stable, right, like my first example today, even if the process is stable, look at the numbers, right? Are you happy as a company with numbers like this, right? With numbers like 0.8%, 0.5%, 0.6% defective. Can you live with that, right? Because again, if you're manufacturing heart defibrillators, maybe you'll want your tolerances to be very, very low, right? Maybe you would set it up so that you'd we're gonna change things until the probability the percentage of our defibrillators that are defective are less than maybe 0.5% or a 1/4%, right? It depends on what you can live with. It depends on what company to company, what the company specifications are, right? So again, even if it were stable, which is not, right? This particular one wasn't because of that 11th day. But even if it were stable, I would still go back and ask myself, am I happy with these numbers though? Sure, they're consistent. Sure, they're stable. But am I happy with them? Are they satisfactory to me? And if not, then I got to fix stuff. All right. Now again, all that stuff about fixing processes and how to fix a process, that changes from company to company, service to service. So I'm not getting into that, right? The whole point of these videos was just to look at a chart, an R chart, an X bar chart, a P chart, some control chart, and just determine whether or not a process was in statistical control or not, right? Determine whether a process was stable or not. And that was it, right? And how to fix things, why you would fix things, really wouldn't be up to you. Right? It would be up to each individual company, each individual service that was being monitored. All right, so I hope this video was informative. Hope the examples made sense. The formulas were easy to follow. And again, I hope you enjoy practicing problems of this nature. Right? The only way you're going to get good at this stuff is by practicing. And thank you very much for watching.